I'm going to write down something down called the increasing function theorem next. And your book states a couple versions of this. For the sake of simplicity, I'm just going to state one version of it. And I'm going to go ahead and use the notation that I use with the mean value theorem. If f is once again a function whose domain is the closed interval from a to b and whose codomain is the set of real numbers, is continuous on the open of the closed interval from a to b, differentiable on the open interval from a to b. So it's starting out just like the mean value theorem does. But there's an extra assumption here, and f prime of x is positive for all x in the open interval from a to b. And notice, if I say f is only differentiable on the open interval from a to b, then I can only have an open interval there too, because f prime of a and f prime of b may not exist. And there are such examples. The conclusion is then f, this function, is increasing on the closed interval. And I'm going to add the word strictly in there in parentheses. The book doesn't include that, but I like to. Strictly increasing on the closed interval from a to b. If you think about the meaning of this, it should make sense. What is it saying? If you know you've got a nice function, graph is continuous, don't pick up your pencil, differentiable, it's smooth, the derivative exists on the open interval, maybe not at the endpoints. How could that possibly not exist at the endpoints? Maybe you've got vertical tangents at the endpoints. That's one way it might fail to exist at the endpoints. That does happen. And if the derivative is always positive, so the slopes of tangents are always positive, doesn't it make sense the function should be going up? Seems pretty intuitive. However, proving it is not easy. I'm going to go ahead and show you the proof. The book does this proof as well, though my style might be a little different than the book. You need to understand, first of all, what it means for a function to be increasing over an interval. Always going up. Its graph is always going up over the interval. What does that really mean? It's actually less clear than you might think at first if you draw a picture. And you can't just draw a picture and say, hey, look at the picture. That's not good enough for a mathematical proof. It might be good enough to convince somebody, but it's not good enough for a proof. We need to give an argument without pictures. Here's the way to start it. Suppose you've got two numbers. Call them x1 and x2. Suppose these are in the closed interval from a to b with x1 less than x2. What are x1 and x2? I'm not saying. Other than the fact that they're in the closed interval and x1 is less than x2. Why am I doing this? Because if I could show, mathematicians often speak in third person actually, if we can show that f of x1 is less than f of x2, then we will be done. Technically, this statement is not necessary to put in the proof, but I think it's helpful. This statement here, based on the assumption that x1 is less than x2, is what you need to do to prove the function's increasing over the interval, over the entire interval. And it really is the arbitrariness of x1 and x2 that guarantee that this is good enough. to prove it. They really do have to be arbitrary. You could have a function that increases for part of the interval and decreases for another part of it. And this thing that I'm trying to show could be true for some x1s and x2s, but not other x1s and x2s. Oops, x2. For the blue x1 and the x2, you can see the second coordinate of the second point there, f of x2, is bigger than f of x1. But for the green ones, it's a little hard to tell, but I purposely tried to make f of x2 a little smaller than f of x1. Green and blue look too much alike here. I think I should have used red. So if your function increases and decreases, the exact location of x1 and x2 matter. To know it's truly increasing over the entire interval and not decreasing at all, they need to be arbitrary numbers in the interval. And this first sentence effectively does that. I'm not saying what they are. Therefore, if I can show this, it's good enough. So that's part of the battle, is realizing what you need to show. The other part of the battle is how. How do I do that? I don't have a formula for f. I drew a graph there, but that's not what the graph looks like. I have no idea what the graph looks like because it's a very abstract statement. So how in the world can I do this? It's the mean value theorem. And what else? Well, let's just play around with it and see what we can conclude. This is stated in such a way that the mean value theorem hypotheses are satisfied. Function is continuous on the closed interval and it's differentiable on the open interval. Therefore, the conclusion of the mean value theorem will be true. There will be a number c between a and b, where f prime of c equals f of b minus f of a divided by b minus a. Okay, I could write that down, but it turns out to be better to apply the mean value theorem to the function over the interval from x1 to x2 instead, because that's related to what you want to show. By our assumptions, we may use, I'll say apply the mean value theorem to f, not on the original interval from a to b, but on the smaller interval from x1 to x2, to conclude there exists a number c in the open interval from x1 to x2 such that f prime of c equals f of x2 minus f of x1, all divided by x2 minus x1. The theorem, the increasing function theorem, is set up in such a way that it's like a big hint, a big green flashing light saying, hey, maybe try the mean value theorem. Try applying the mean value theorem. Of course, that just begs a question. How do you prove the mean value theorem? We're not proving it because if you prove it from scratch, it takes, well, if you prove it from the basics of arithmetic, it takes an entire semester to prove. If you prove it from some higher level than just basic arithmetic, you can prove it within maybe a month of classes. I'm serious. And we actually have a class where they prove it. It's called real analysis. So it's not something trivial to prove. You have to go from more basic foundational principles to know you can prove it. We don't prove it in this, but we use it to prove other things like this. Okay, so that's great. How's that helpful? This should, if you stare at this long enough, seem like maybe, just maybe, it's helpful. Why? Oh, I see an f of x1 and an f of x2 in there, and that's what I'm trying to show that relationship right there. Maybe this is helpful. I don't see a less than or greater than sign though, so maybe not. What else might be helpful? How about this fact? I never used that fact yet. I'm assuming it to prove the theorem. To prove a theorem, you assume the parts that come after the if are true, and you show the conclusion follows. The parts after the if are called hypotheses or premises. The part after the then is called the conclusion. I haven't used that assumption yet. I guess I could apply it to C, f prime of C. By assumption, f prime of C is positive. Oh, there's an inequality. So f of x2 minus f of x1 divided by x2 minus x1 is positive. This feels like we're getting close. So I got the ratio of two things being positive. That means one of two possibilities. Either the numerator and denominator are both positive, in which case I'd be done, because this being positive would mean this is true. Or they're both negative, which would mean the opposite of what I'm trying to show. So how do I know which case this is? Are they both positive or are they both negative? Well, I do know that x1 is less than x2. I assumed that. Since x1 is less than x2, it follows that x2 minus x1 is positive. Right? If 4 is less than 7, therefore 7 minus 4 is positive. Therefore, 3 dots means therefore, f of x2 minus f of x1 is positive. So we're done. F of x1 is less than f of x2. QED, praise the Lord. We are done. Smiley face. Will you have to do such a proof on the test? Not from scratch. Maybe I would show parts of the proof and you might have to fill in the blank for reasons. I think I've done that once or twice in the past. It's been rare, but I'm not ruling it out. You should be able to give reasons like mean value theorem or assumptions or something like that in various spots. There's a decreasing function theorem as well. If f prime is negative in this case, then f is strictly decreasing on the interval. There's a constant function theorem as well. If f prime is always equal to 0 on the open interval, then the function's constant. Its graph is horizontal on the interval. All these things can be proved with the mean value theorem. In chapter 4, we can also prove something very important called the first derivative test. For maxima and minima, that's going to be our main focus next Monday, though we will do some more about linear approximations.